So far we have discussed sets, set operations or set algebra, sequences and subsequences of sets, their limits, lim sup and lim inf, and indicator functions and related results. In this lecture, I will try to give an idea or try to extend the idea to field, sigma field, and one special type of sigma field called Borel field. This will give us a platform on which we will define measure space and set function, measure, and so on. We will be discussing field or sigma field with some examples. We will also try to establish the relationship between sigma field and monotone class. This will be helpful to find or to define the set function, which will be in our next slides. Let us start with the definition of class. So far, we have defined set as a collection of elements. Now, class is once again a set, but it is a set of sets. That means all the elements of a class are itself sets. So, set of set is known as class. Then we defined a field. A field is a non-empty class. We denote it as script A, which of subsets of omega. This is the universal set. We call this as a field if it satisfies two conditions. The first condition we call is as closed under complementation. That means if A belongs to script A, that implies its complement, that is A complement, will also belong to script A. We call this property as closed under complementation. Then the second property that it has to satisfy is that for two sets A1 and A2 both belonging to script A, that will imply their union A1 union A2 will also belongs to script A. We call this as closed under finite union. So, I am considering two sets, but we can have finite number of sets A1, A2, A3, AK, then their union will also belong to A. If any non-empty class satisfies these two conditions, then that class will be called a field. So, one interesting thing is that what is the smallest field that we have? The smallest field that we have is a collection of phi and omega. Why is it so? Let us check the first condition. Phi belongs to A. Now, its complement, phi complement is a universal set, it also belongs to A. So, this class is closed under complementation. Now, if I take the union of phi and omega, that will be omega, and omega once again belongs to script A. So, it is closed under finite union. Since both these conditions are satisfied, this is the field. Not only field, it is the smallest field. Now, if script A is a field, then we say that phi belongs to script A and omega belongs to script A. So, for any field, these are the two elements which will always be there. Now, if A belongs to script A, that means A complement also belongs to script A. Because script A is a field, then it is closed under complementation. It is closed under finite union too. So, A union A complement will also belongs to script A, and A union A complement means the universe, that means the universal set belongs to script A. If universal set belongs to script A, its complement will also belongs to script A. So, complement of omega is nothing but phi. So, null set also belongs to script A. So, phi and omega, they are two elements which will be always be there. Now, if A1 belongs to script A and A2 belongs to script A, we want to see that whether their intersection belongs to script A or not. It belongs to script A too. The proof is very easy. So, if you take A1 intersection A2 whole complement using De Morgan's law, we can say that it is A1 complement union A2 complement. We know that A1 complement belongs to script A, A2 complement belongs to script A, and their finite union also belongs to script A. That means A1 intersection A2 belongs to script A. So, it is closed under finite intersection 2. We have the smallest field omega and phi. Now, we want to find the smallest field containing a set A. What should be the smallest field? We have already proved that phi and omega will be two indispensable sets belonging to this class. So, sigma A is the smallest field containing A consists of 4 elements: phi, A complement and omega. We will try to discuss a few more examples. Suppose we are considering a class script A is a collection of all those sets A, where A is a subset of omega, this is the universal set, with A is finite or cofinite. Now, we will define what do we mean by cofinite. A is called cofinite if A complement is finite. Consider the universal set x1, x2, x3, xn and so on, and I define An as a singleton set xn. Now, An complement is cofinite because complement of An complement, that is An, is finite, is singleton set. So, An complement is cofinite. Now, suppose A and B, these are the two sets belongs to script A. Now, we have to show that it is closed under finite union. That means A union B belongs to script A. If A and B both are finite, we do not have any issue, because if A is finite, B is finite, their union must be finite. And in script A, we have all the sets which are finite or cofinite. So, A union B will be finite and they belongs to script A. Now, what will happen if at least one of them is cofinite? If at least one of them is cofinite, that means their union will also be cofinite. Now, we will take A union B whole complement is A complement intersection B complement. Now, both of them are if they are both cofinite, then A complement will be finite, whereas B complement will also be finite, their intersection is finite. If at least one of them is cofinite, then their complement will be finite. So, once again the intersection will be finite. So, that means A union B belongs to script A. So, that shows that script A is a field. Now, consider another example. Here we are considering the real line as our universal set, and we are considering a few intervals. Now, if you see, the intervals are defined in this way: minus infinity to x, x belongs to script R. This is a real line. We define two sets, A which belongs to script A. So, the A set says it is an interval minus infinity to x1 and B is an interval minus infinity to x2. Now, it is clear that both A and B belongs to script A. If you take the union of A and B, it will be minus infinity to maximum of x1 and x2. Once again, it belongs to A, script A. So, script A is closed under finite union. What about the complementation? If I take the complement of A complement says it will be an interval ranges from x1 to infinity, but note that this interval does not belong to script A. So, it is not closed under complementation. So, script A is not a field. Once we have the notion of field, now we want to extend this field, the notion to what do we mean by sigma field. Well, sigma field is definitely a field. It is a non-empty class F, script F of subsets of omega. We call this as sigma field if, like field, it satisfies two conditions. The first one is the same, that it should be closed under complementation. That means, if A belongs to script F, then A complement will also belongs to script F, that we have seen in the previous case also. And the second part is that for every sequence of sets A n, if A n belongs to script F, their union will also belongs to script f. So, it is called closed under countable union. So, the main difference between field and sigma field is that the second condition, where in field it is closed under finite union, it has been extended in sigma field to countable union. So, sigma field is an extension of the field. So, we say that f is a sigma field. If f is a sigma field, then f must be a field. The question is whether the converse is true. Now, we will give it one example. The example that we have just demonstrated, that omega is a collection of x1, x2, xn, script f is collection of those sets which are subsets of omega, and A is finite or cofinite. So far we have proved that script f is a field. Now we consider a n. We define a n as x to n. That means a n is a sequence of those elements. So if we put n equals to 1, a1 is x2, a2 is x4, a3 is x6. So I am taking only the even elements. A n is a singleton set. A n belongs to script f. We do not have any problem to understand that. But whenever we are taking the union n from 1 to infinity a n, that means we are taking the elements x2, x4, x6 and so on. This does not belong to script f. The question is why? Because this set is neither finite nor cofinite. It is an infinite set. It is not cofinite because if I take the complement of this set, that means I will be taking the odd numbers x1, x3, x5. Once again, this is not finite, this is an infinite set. So that means even if script f is a field, it is not a sigma field. Now we will define what do we mean by monotone field. We say script f is a monotone field if this a1, a2, an and so on, these sets belongs to script f, they are monotonically increasing in n and their limit is a, then a will also belong to script f. And if they are monotonically decreasing, we denote this as a1 star, a2 star, an star. These are the sets which are decreasing in n and it goes to its limit a star, then a star will also belong to script f. So, if these conditions are satisfied, we say f is a monotone field. Now, what is the relationship between monotone field and sigma field? We can say that every sigma field is a monotone field and every monotone field is a sigma field. How to prove this? Well, we will start with the assumption that let script f is a sigma field. Suppose that a n is monotonically increasing, and we know for increasing set its limit goes to its union. So, a will be union over a n, and if its decreasing sequence, then its limit will go to its intersection. Now, a n belongs to script f, that implies union over a n will also belongs to script f, because script f is a sigma field, and if script f is a sigma field, it is closed under countable union, and union over a n is nothing but the limit. So, a belongs to script a. Suppose a n star is decreasing in n and its limit goes to a star, and a star is nothing but the intersection of all these sets. Then a n star belongs to script f. We know this. This will imply their intersection will also belongs to script f, and that means a star belongs to script f. Hence, we say that script f is a monotone field. So, if script f is a sigma field, it is a monotone field. Now, we will try to prove the converse, that if script f is a monotone field, whether it is sigma field or not. Now, take a1, a2, an, these n sets, they belongs to script f, and we define bn k from 1 to n a k, and it belongs to script f, and cn is the intersection k from 1 to n ak S belongs to script f. Now, one thing we should note that as n increases, Bn also increase. So, Bn is a sequence of, or Bn is monotonically increasing, whereas Cn is monotonically decreasing. So, we know the limit of an increasing sequence will go to its union, and limit of a decreasing sequence will go to its intersection. So, B will be the limit of Bn, which will be k from n from 1 to infinity n, and Cn is a decreasing sequence, and its limit will go to C, which is intersection of n from 1 to infinity n. And note that B and C both belongs to script f. So, that means script f is closed under countable unions and intersections, hence it is a sigma field. So, if it is a monotone field, it is a sigma field. If it is a sigma field, it is a monotone field. And one important result is that any finite, countable, arbitrary intersection of sigma fields is also a sigma field. This is one very important result, that to get the smallest sigma field, we can take the intersection of all the sigma fields to get the smallest sigma field. Now, we will try to give an idea about one special sigma field we call Borel field or Borel sigma field. We consider a class of intervals defined by C1 as minus infinity to x, x belongs to R. This is definitely a subset of script R. C1 is closed under finite unions. It is easy to note, but not complementation. Now, we consider the smallest sigma field contained from C1. We defined it as script S C1. Such sigma fields contains the set of type we call Borel field. This sigma field is called Borel field. We defined is by script B, and it contains different sets like x to infinity, where x belongs to script R, intersection n from 0 to infinity, and the interval is infinity to minus infinity to a plus 1 over n. Then we have this a to infinity, a belongs to script R, or you can have minus infinity to b and a to infinity, a less than b, b belongs to R, and so on. So, we can have so many sets. All these sets are called Borel set. So far in our day to day life or in our courses, whatever sets we will be using are all Borel sets. There are some sets which are not Borel, but that is beyond the scope of this lecture. Starting with the definition of class, we define field, sigma field, and Borel sigma field. We have tried to give you some examples of these fields and Borel field or sigma field. We have also proved the equivalence relationship between monotone class and sigma field, and this will be the best to define set function or measure, which will be described in later slides.